Hello, everyone. My name is Sahar Asadi, and I'm a senior machine learning engineer at ClusterOne. And today I'm going to present you a tale of a scale. And in particular, I will talk about distributed TensorFlow. Okay, let me start first with telling you my story. It's a lot similar to what we heard in the previous presentations, but it's a true story that's about my experience. So this is me when I was a PhD student, and I was studying computer science, and I had a focus on applied machine learning. And in my mind, back then, applying machine learning was to find a very interesting problem, apply the most recent machine learning methods, and iterate over and improve it and publish it. And of course, I was making a lot of assumptions to get rid of the constraints, and also I was using clean existing data sets. So 2012, I started moving from university to industry, and this is me now. And during this time, I've been working in different companies, Oculus AI, Meltwater, and Spotify, and now in ClusterOne. And as time passed, I worked in different problem spaces, and I worked with different type of data, different machine learning infrastructures, different machine learning methods. And as time passed, I realized this happy moment that I had as a graduate student about building machine learning models is only a small proportion of the time that I spent at work. So as a data scientist or a machine learning engineer or a researcher, when you're building a machine learning model in industry, you are dealing with data collection, ETLs, modeling, training, iterating over, analyzing, and finally serving that model. And, well, I mean, I know that it's good to know a lot of engineering concepts, but of course, I would like to spend my time where I have the most added value for the company. And you know, you end up spending a lot of time on setting up environments, setting up pipelines, building models, training, visualizing, and scaling, besides to, of course, data collection, ETLs, model serving, understanding the problem space, and metric definitions. And ideally, I would like to have a setup where I don't need to spend time on this setup and infrastructure challenges. And I also can share with my colleagues what I do, collaborate, analyze, understand, improve my model. And this is where ClusterOne is focused on, to have a kind of operating system for machine learning by covering these three aspects, the three green boxes in the middle. You know, in industry now, a lot of companies are starting working using machine learning. There's a lot of data, there are a lot of existing models, and a lot of state-of-the-arts like growing. And for especially smaller companies, the challenge is find better models faster and cheaper. And this is the motivation for this presentation. What I will cover in this presentation is first I will introduce you to ClusterOne, then I will talk about deep learning on distributed infrastructure, and I will in particular focus on distributed modeling using TensorFlow, and I would like to have some discussions at the end. So, ClusterOne. ClusterOne is a startup launched 2 years ago, and it has been backed by Allen AI Institute, and I'm part of the applied AI team in this company, where we do both research and we also support customers to build their machine learning solutions and scaling their AI strategy. And we are now spread around. We have team members in Seattle, San Francisco, in Poland, in Canada, and of course in Stockholm, where I am. So the focus in ClusterOne is to scale your AI. So make AI development at the scale easier and more efficient. How we do that? In ClusterOne, we enable accelerating your research by taking advantage of scalability and distributed training to speed up model development and research. And then the second part is the aim for having zero DevOps. Instead of focusing on the DevOps work, focusing on modeling and being able to contribute more as a data scientist. And finally, it's about total infrastructure freedom. So we are supporting different infrastructures. In other words, our platform is infrastructure agnostic. And this helps a data scientist team to be able to try and test different infrastructures and not to limit themselves to make an early decision. So getting back to the stages of machine learning, by using ClusterOne, we are trying to enable spending more time on high-value problems by addressing the setup infrastructure, run distributed experiments, tracking results, and sharing experiments. In ClusterOne, you can build your code, and you can commit different versions of your code available on Git, and also you can share your code or data set with your colleagues, and you can look at the analysis on the integrated tensor board, and you can also see your jobs and projects in the graphical interface. So if we look at the ClusterOne as a platform, it supports using a lot of different apps and deep learning tools. For example, Chainer, TensorBoard, Jupyter, PyTorch, TensorFlow. And it also provides you interfaces that you are familiar with, APIs, graphical user interface, and the command line. And it takes care of the OS level type of works. For example, Kubernetes, orchestration of your jobs, firewalls, monitoring, and job management. Also, it supports different type of infrastructures. You can use common cloud solutions, small cloud providers, or on-premise installations. And you can have different artifacts integrated. Here you can see an example of using APIs. Our graphical user interface, this one is kind of old because next week we are going to release a new version of our graphical interface. And then in the command line, our command is just. For instance, here you see just create job distributed, your project name, data sets, and number of workers and parameter servers. And then you can start your job. So let me go back to deep learning on distributed infrastructure. Here, I assume that you're familiar with TensorFlow or similar frameworks for distributed machine learning. So just a recall, our goal is to find better models faster and cheaper. So, and this is exactly why we need distributed deep learning. Distributed deep learning is used for different purposes. One of the use cases, one of them is, for instance, when you want to train more models in parallel. For instance, when you want to do hyperparameter tuning of a model, and you want to compare different models with different configurations. And in this case, we call it experiment parallelism. Then another example is when you want to train bigger models that they don't fit, for instance, on your GPU. Then you go for model parallelism. And another case is when you want to train faster because you have larger data that you want to try on. And we call this data parallelism. Let's go over each of them. Experiment parallelism. In experiment parallelism, as I said, you want to run a model with different configurations on different machines. So here we have 4 machines, same model, different configurations, and you want to know which one is performing better. Second one is model parallelism. And in model parallelism, basically, your model is too big to fit into one GPU, for instance. And what you do is that assign different parts of the graph to different machines. Here, you see that each layer is dedicated to, computation, each layer is dedicated to one of the GPUs. But note that this doesn't necessarily speed up. It helps to train larger models, but doesn't necessarily speed up because computation operations in each layer executes after the previous layer operation is done. So let's go to data parallelism. Data parallelism, as I mentioned, is for training, for instance, your models faster. And what you do in data parallelism is that you have the same model in different workers, and you give them different parts of your data. And they send the updates of the weights from each of them are sent to update the model. This is one of the most common ways, and it's like one of the easiest things to do in parallelism, and that's why I focus on data parallelism here. So the common approach is, in this data parallelism, is parameter server worker model. There, you divide your devices into two groups, parameter server and worker. A parameter server is responsible for holding all model parameters and updating them in response to incoming gradients. And workers do the heavy lifting. They are responsible for input processing, calculating the loss, and performing the backpropagation and sending updates to the parameter servers. And in workers, we also have a master or chief worker, which is responsible for coordinating between different workers. There are two different ways for data parallelism and in distributed TensorFlow. One is synchronous and the other one is asynchronous. In synchronous, after each of the workers calculate the gradient update, they will be averaged first, and then the model will be updated. So then this means that in order to update the model, first all workers should finish their calculation. In the asynchronous, as comes from the name, the workers send updates independently and don't become idle. And there are papers that they show that the asynchronous approach can lead to good performance. And here I will talk more in particular about the asynchronous approach. How to implement it in TensorFlow? The very first thing is that you need to define a cluster, and you do it with tf.train cluster spec, where you pass the address and the specification of all of your devices. And then, when you have the cluster object created, you are going to set up the server and passing the cluster and specifying each of your device responsibilities. As the next step, you define devices and assign operations. So in the case of parameter server, as you can see on the top, you have the responsibility of weights and bias holding. And then for the worker devices, we have calculations of the model. And finally, you need to configure and launch. So you call your node to join the server, and then you call tf.train.replica device setter in order to assign the operations for the workers. And finally, you need to replace the session.run with monitor training session in order to coordinate all the sending out the summaries to TensorBoard and collecting checkpoints and taking care of the steps that are calculated. How to run it? So you run your code with different parameters based on if they are workers or they are parameter server. Of course, if you have a good infrastructure, you don't need to go through this trouble of running them individually, and you can just tell your platform to go and dispatch this job on all the workers and parameter servers. That's what we do in ClusterOne. Here is an example of running transformer on the Opel SLR dataset, and we trained it on our platform. This is not the most optimized result, but it's just I'm putting it here to show you the differences. The blue line here is for a single node, and the red line here is for using 32 workers. And you see that, it provides you a speed up. But in order to optimize this speed up, there are a lot of factors like batch sizes, model structure, how you deal with your data, and a lot of parameters that you can optimize this better. So let me tell you also about another experience. The first time that I started working with TensorFlow, it was like a horror movie to debug the code, because it's hard to debug, and it also has deep stacks for tracing. And ideally, you want to find ways, if you can get some intuitions of what has gone wrong in a distributed computation, because even in single node for me it was difficult, let alone when it's distributed. So here I'm sharing some of the tips and tricks that I've learned. So first one sounds very obvious, but believe me, working with a lot of customers, I know that it's not very obvious. So the very first thing is that to have a small subset of your data ready in order to test, just making sure everything works, and then going to scale and use the whole data that you want to originally use. And then for diagnosis, we usually suggest to first run on a single node. And if it works, then move to a distributed one. And for distributed, there are a few a few items in the checklist that you can check. First question is that does the job fail at the same time or on the same batch? So looking at answering this question, you might get some intuition if this is because a corrupted data or a memory leakage. The second question is that does this fail during a specific operation? For instance, it could be an issue with storing and writing when you are using checkpoints, and then you need to explore further. And finally, it's also about, does always job fail because of the same worker? Because it might be the case that you have set up one of your workers wrong. And the most important thing I would say is that to find out if the problem is because of a bug in the code or a problem on how you are utilizing distributed system. And in order to do that, we have added something to our Python package to emulate running a distributed job locally on your system. And this is the syntax that we use. We just do just run local distributed and the project that we work on. And this helps a lot to identify what's the issue in a distributed problem. So also, given the nature of a distributed job and using parameter servers and worker model, potential causes are networking, because all workers and devices need to be able to communicate, and it could be because of a missing pod, and it could be also because of bad initialization. And the last one is the one that I usually make mistake on. And if you have a good infrastructure, should be able to deal with this. It should be able to be fault tolerant and do all the clearing logs and so on for you without getting to these troubles. And then also be aware of known issues. For instance, if there is a framework, for instance, TensorFlow certain version doesn't work properly with the type of distributed infrastructure that you want to use, then be careful and check for this in Google. And then, of course, you want to scale and you want to speed up, then the next question is about what should be the ratio of parameter server and workers. And this is something that is not easy to do, reason about, and you need to do a lot of benchmarking, and having an infrastructure to support that would be really good. So to summarize, it's really helpful to have the right infrastructure and be cautious when you are debugging your code in distributed calculations. So parameter server worker model has is very good, showed a lot of improvements, speeding up calculations, but it does also have some limitations. So one of them is requiring for you to change code. It's becoming more and more obsolete, because the new releases are supporting better for you with high-level APIs, so that you don't need to change a lot your code. And the other thing is the issues with parameter server. And when the number of workers scale up, we will have bottlenecks with the parameter servers, and we might also have saturated network when we increase the number of parameter servers. And it also requires a proper infrastructure setup. So we talked about data parallelism, we talked about parameter server worker model, but there are also other ways, and it's good to have a look at the landscape of distributed deep learning. There are a lot of works, even just the past 1 year, that are focused on architecture and some on algorithms. Example of architecture work is better APIs for multi-GPUs and multi-node multi-GPUs. And also, in terms of algorithms, there are a lot of algorithms developed to efficiently run all reduce and gradient updates. Here is a graph published by O'Reilly that shows running training time for ImageNet and different type of infrastructures used and how much time it takes. But I think, don't rely only on this one, because working with different customers, what I've seen is that the right choice of infrastructure, even if you find the best one, doesn't necessarily speed up a code if it's not set up properly, or the code or the model doesn't fit into the infrastructure that you are planning to use. Getting back to algorithms, also let me talk a little bit about all-reduced. All-reduced doesn't require parameter servers, and each worker communicates to all other workers and trains the model using the part of data and stores the weight and bias. And what happens is that the gradient update is in a synchronized manner, and you might think that this slows down the speed that we are gaining with parameter server worker asynchronous. But if you use this on a small number of machines or multiple devices on a single machines, like NVIDIA devices with GPUs, this is a good case for improving the performance. And there are several algorithms published that efficiently combine gradient updates in all-reduced. Mirrored strategy is one that was presented this year in TensorFlow Summit, and it's one of the examples of distributed strategy. It's easy to use, and it's basically one-liner change in your code. And Uber released Horowod, which is based on OpenMPI, and what it does is that it helps when we are at a scale in the performance. You can see here, this is distributed TensorFlow, and this is Horowod when we use like larger number of resources. So, to finalize, what I want to say is that there are 3 design challenges to consider when you are deciding what kind of distributed solution to use. The first one is performance. So the question to ask is that whether or not you gain the speed up that you want compared to a single node, and if there is like a cap to your scalability. The other one is switching cost. So as a data scientist, I usually don't want to change my code, and also I want to know how much I need to change my architecture. And finally is about infrastructure, and you need to know if it requires a specific technology or certain knowledge of infrastructure in order to use certain design. So keep in touch. We usually have Coffee with ClusterOne. It's a webinar series that we run, and you can watch them also on YouTube. And yeah, feel free to ask questions and get in touch with us. Thank you.